hands on deck, all hands on deck. Today on the SS L'Hôpital, we're going through some rough waters and howling winds. In order for you to help us navigate around Cape Horn, we're going to teach you how to use potential functions.
Let us rewind. Background of potential functions. Potential functions give us a function described by a given vector field f, where f is equal to the partial derivative of the potential curve with respect to x, comma, the partial derivative of the curve with respect to y. So potential functions show the work done by the vector field on a particle over an interval. So in this scenario, the work done is the potential curve of the wind on our ship, where our ship is the particle moving through the ocean. So when do we use potential functions? We can use them when the vector field f is conservative, which can be written as m comma n, breaking it into the parts. F is conservative when my equals nx, or fxy is equal to fyx. This is also when the curl of the vector field equals 0. Back on board the SS L'Hôpital, cornering the Cape, our first matey has just figured out how to represent the wind as a vector field. Now, we must find the potential curve.
Aye, aye, mateys. I have determined that the wind can be represented by the following vector field. F equals 2xy, comma, x squared plus 2yz, comma, y squared plus 2z. We can denote each of the terms of the vector field with L, M, and N for simplicity. So to find the potential curve, little f, we're going to need the integral of L with respect, dx with respect to x. So this is going to equal the integral of 2xy dx, which equals, taking the antiderivative, we're going to end up with x squared y. Because we don't have bounds, and this is a generic integral, we're going to need to take adding a constant c, which will be in terms of y and z. Now we need to find c of y and z. So we have c in terms of y and z, and now we're going to use the middle term, m. That's going to equal the integral of m, which is x squared plus 2yz with respect to y. And if we solve for that, that's pretty simple, and we're going to end up with x squared y plus y squared z. Now it's important to note here that we have a repeating term. We have an x squared y term here and an x squared y term here. When terms repeat, we don't need to repeat them in the potential function. So this leaves us having y squared z as c in terms of y. And again, because there are no bounds and it's generic, we're going to need to add c in terms of z. So to do that, we're now going to use the third term, n. So c of z is going to equal the integral of y squared plus 2z with respect to z, which equals y squared z plus z squared. And again, we're going to have a repeating term. We're going to have y squared z here and y squared z here. This means we don't need to repeat them, so we're left with z squared as our c in terms of z. Combining all of the not-like terms together, that is all the terms that don't repeat, we're left with our potential function, little f, and that's going to equal x squared y, because we're going to keep one of those terms, plus y squared z, because we're going to keep one of those terms, and we're going to add to that z squared. And that is our potential function.
This production of Dorm Room Professors was brought to you by Santa Barbara Surf Shop.
in the beautiful city of Santa Barbara.